So we have three speakers in this session, and actually looking at the speakers, I'm kind of reminded like I'm in the pit lane of the Indie Autonomous Challenge, because these are people I've spent several months with the students in these teams, especially for Marko and Alex. And we are very glad that they'll be joining us and talking about their experiences of doing full-scale autonomous racing. So starting with Marko Bertogna, he's a professor at the University of Modena, where he leads the HiPeRT Lab. Marko is no stranger to autonomous racing. He has been part of the autonomous racing community since more than 5 or 6 years ago, in the early days of the F110 competition. I also noticed some of his students are here at ICRA. They'll be racing in the F110 race over the next couple of days as well. And he does research on real-time systems, autonomous driving, industrial automation. And he's also the leader for the Euro racing team, which is one of the few teams which have competed in the full scale in the autonomous challenge. And his team is consistently among the top 2-3 teams in that competition. So Marko, I'm going to make you the host so that you can share your screen. And you can
Madhur for the nice introduction. Just a quick mention who we are. So the lab, as you properly recalled, works at the intersection between real-time systems and autonomous platform, autonomous driving. So we do have many different cars, not only cars. We work in multiple domains. Lately, we have been working with our main partner, TII, on autonomous drones, not only aerial, but also water drones and underwater drones for many different challenges. Let me first start reminding what happened in Indianapolis, right? So as you recalled, I'm not sure whether the audio is also can be heard from your side, but here we can see what together we achieved during the Las Vegas challenge. These are our friends from Munich overtaking us at high speed. On the right, you have what our stack was visualizing also remotely. And yeah, the different decision on the path. So here you can see our turn in overtaking them. It's nice just to remember those good days back there, days that we'll be living again in next November. And here you can see our car overtaking Munich one, I guess at 230 kilometers per hour. And that's it. Okay, so what was that introduction for? So I'm not a control guy, okay? I'm more kind of an embedded system engineer, professor of real-time systems and so on. So my point of view is more on the architectural side, on the embedded side, and on the latency of the robotic software. We like to play with the next-gen embedded platforms, and we like to advocate their use community. So much like when we do, who's drawing here? I don't know. We like when those architecture are being pushed to the limit of whatever they could deliver in real time. Essentially, we don't think that the current platform of the Indie challenge was so embedded, as you can probably notice by the list here on the right. So we did have a Xeon server. We did have a discrete GPU, was a Quadro 8000, not properly embedded. And we did have like some Cisco switch, which took forever before turning it on and so on. So it was an excellent car, an excellent capabilities could be proved with it, but let's say that the computing platform was not so suitable to optimize latencies, okay? So not optimizing latencies entail to a lot of problems in the perception to action path, which is exactly where we mainly focus at. So what we did, we decided together with our spinoff, HiPeRT, has the same name of the lab, to design an alternative solution on another car. This was an F3 car that we entirely reconfigured for embedding our this time small controllers. And also while we did that, we tried to minimize all different kind of actuators, leaving the space for a potential driver, or maybe if the driver is there not to drive the car, for a safety man that is able to recover the car in case it is needed. But of course, if you leave space for the driver, you need to compact out everything else, source, actuators, and you name it, and computing platforms. You know how difficult is it to, and you also know those that participate to Indy, how bulky were the computing platform and actuators we had on the car. So it was quite a difficult job that we did, and we're also happy to share it with whoever would like to do something similar. But at the end, we were able to cram different GNSS, big LiDAR here on top, similar to the Formula Student platforms. We did integrate all the actuators for steering wheel, brake, accelerator, shift. We did have a couple of cameras, phonic wheels, and so on. The point is, we needed to put a computing platform that was able to do whatever we did in Indy, just at a way smaller size. So the embedded board should fit just here, the top, the front part, the frontal part of the car. We decided to go for an NVIDIA Xavier, and I am sure half of you guys know pretty well what do the NVIDIA platform, how they are made of. Essentially, they use this new computing paradigm, this heterogeneous computing paradigm, mixing a CPU cluster with 8 cores together with latest generation GPUs, programmable vision accelerator, DLA, and so on. This is kind of a different computing paradigm than the Xeon-based we had in Intel, but way more similar to what we are comfortable in playing with. Our typical task is to merge this complex workload-intensive task, the typical one you use for perception, model predictive control, and clustering, Kalman filter, and so on, together with tight real-time latencies. This is very typical instead of the companies that we work with in the automotive domain, and not only in the automotive domain. So they typically require us very strict perception to action loops, age and reaction latencies, and so on. And they often ask us a way to certify it. We don't do certification, but we need to provide them the material towards a certification and at least a safety qualification in case of automotive provider. So we are in this mixed territory between performance-oriented world and the predictability-oriented world. The first world is probably typical in robotics in the previous talk, when we focus more on the algorithmic perspective, on the sensor fusion part, on the planning, and so on. And we kind of assume we have enough resources. Then we try to do our best to fit the computing capabilities we have, but we don't focus too much on the qualification and certification part. This instead, the second world, the predictability-oriented world, people from industry know it very well, and typically is handled by different teams than the robotic one focusing on the algorithm side. And here you have safety critical routines. Also, the way in which you write code is very different to just using a ROS driver or a ROS library. You have functional safety standard, you have certification, ASIL in the automotive domain, the DAL in the avionic one, and so on. Often your programs are asked to comply and are required to comply with strict programming practices like MISRA-C, avoiding the use of dynamic allocation of memory, limited use of pointers, and so on. And everything needs to be optimized for the worst case, okay? And this, of course, is of interest to industry, but is also of interest whenever you would like to avoid the delays that could cause your car to crash in front of a wall, with the consequent bill of materials that in the challenge organizer are asking to the teams whenever something needs to be fixed. Also, I would like to bring your attention to how we can leverage the capabilities of newer generation architectures. So how these are made to be able to squeeze out performances and predictable performances out of them. Essentially, this is kind of a popular slide I stole from somewhere, where the Moore laws, the NARD scaling of and in the computational power of a newer generation architecture is kind of reversed, is kind of brought into an exponential increase in the number of cores. Since 20 years ago, 15 years ago, we are no more able to increase the frequency. So what you notice here is that the exponential increase in the number of transistors is leading to an exponential increase in the number of cores, okay? So reducing semiconductor manufacturing processes below 5 nanometers, 4 nanometers in this year by Samsung, for instance, is delivering 4 nanometers chips, is no more using to increase the frequency of the core. So you don't have just 1 or 2 cores, but you have hundreds or thousands of cores, which are the ones that provide you the ability to maximize performances in your newer generation architecture. Just to mention that we are reaching the limits where 20 water molecules have essentially the same size that you have between 2 transistors in modern architectures. So these parallel computing capabilities is essentially what allows you to squeeze in the equivalent computing power you had in the #1 supercomputer in the world in just a 1 or 2 square centimeter device at a few tenths of watts. The semiconductor industry is also consolidating. So this means that you have ever less silicon providers. So you need to deal with the current architectural trends. You cannot configure your own architecture. The latest generation by NVIDIA we just received the last week is called Orin, and it provides you 200 teraops at 40 watts. So this is a trend that keeps increasing. Just as a comparison, this is the way that automotive controllers were made until today. You can see here, these are Infineon Oryx, which is not optimized for performances, but let's say is the highest performance from the safety domain microcontroller. So meaning it's like redundant, it has fault tolerance, it has always V compliance, but its performance features are limited to these few thousand million instructions per second. Orin had 200 trillion teraops, okay, trillion operation per second. This is a multiple order of magnitudes more. So we are talking about 2 completely different worlds, okay? Bringing one world, the performance-oriented world, to this older generation world is a lot of work. It's essentially what we try to do. Just skipping very quickly to these next 10 slides to show you that it is a consistent paradigm. Heterogeneous computing is the way platform system on chips are made today. You can see the latest generation by Xilinx, multiple core, AI engine, DSP engines, programmable logic. Renesas, something equivalent, 8 ARM Cortex, dual R52, CNN IP, and so on. Qualcomm from the mobile chip, Snapdragon 8880. Now there is a newer generation, Snapdragon 8, is using older generation to support automotive chips, automotive grade electronics. Samsung is doing something similar from the latest generation mobile towards the older generation used for automotive. HiSilicon, this is the provider to Huawei. They're also investing a lot in automotive. These are the computing platform they are using today for their mobile chips, but there will be equivalent also for automotive. And Intel, you probably know Intel acquired Mobileye a few years ago, and Mobileye is keeping increasing their scaling their controllers, providing also here more than 100 teraops at below 100 watts. So what is the bottom line? So you need to deal with heterogeneous many-core systems. You need to cope with multiple cores, and you need to properly and predictably use the accelerator, the available accelerators. Currently, GPU is kind of like the pervasive throughout all the high-end embedded paradigms, but you also have neural processing unit, deep learning accelerator, FPGA, which typically complement the offer at system-on-chip platforms. So performance per watt can only be given by engine differentiation, not by using a Xeon architecture, but using them is not so easy. This is the only way that allows you to scale from a trunk full of server to what we, for instance, showed in our urban autonomous driving cars, or our or also like people is at a smaller level doing in Formula Student, or we are trying to do it with our Formula 3, or we are also trying to do at different kind of drones domains. The point is applications need to be redeveloped using parallel programming models. So it's not simple to take your C routine and parallelize it properly to take advantage of all available computing, parallel computing resources. So your tasks are likely to be made by a big DAG, DAG, okay, directed cyclic graph. Here is just a small example of just a macro block of our oldest autonomous driving setting, where you can typically recognize the LiDAR processing, camera processing, and then you have the fusion, and then later on you have the planning, and on and on and on. We have identified all the end-to-end latencies between the sensor acquisition towards until the end of the actuation loop to the actuators available in the car. And this is what the OEM and tier ones working with us are typically asking us. The typical latencies are called age and reaction latencies, which OEM typically focus at. So how long an input affects an output of a task chain. This is the age latency. And reaction is essentially something that measures the reactivity to a change in the input when a new obstacle, for instance, comes into your field of view. And for instance, in Indianapolis, one of the problems we had was also related to a long chain of from radar processing until the end of actuation that led us to something not so stable from a control perspective, and we lost track of the car. I don't want to focus on that story. I prefer to bring your attention on how difficult is it, the scheduling problem for this new generation architecture. On the right, you have the platform I mentioned before. So multiple host cores, a GPU, a DLA, deep learning accelerator, programmable vision, and so on. And here on the left, you have your application composed of multiple DAGs with multiple recurring characteristics, multiple periods, multiple end-to-end latency, multiple deadlines, and so on. So how do we partition and schedule all these DAGs onto the available platform such that deadlines and real-time guarantees are met? Add that there are a lot of unpredictable mechanisms and factors in your architectures. Memory is becoming a nightmare from a predictability perspective. Memory speed is stuck since back 20 years ago. We didn't have any improving memory speed. We did have larger memory bus, but the latency in acquiring data from memory is stuck, okay? So we did a lot of experiments showing the latency in memory in unfavorable scenario can be up to 100 times higher than in the regular case, okay? So think about this when you need to qualify your system, when you need to prove tight real-time guarantees. Going to the end, so we are also trying to address this allocation and scheduling problem, okay? So try to cram your multiple DAG system onto the available computing platform. This is also the subject of Minerva. It's another spin-off that we founded with our colleagues in Munich and our colleagues in Boston and Waterloo. It also provides an heterogeneous systems of hypervisor and operating system, which is compliant with the typical requirements. And we proved it in our autonomous car. You can see that opening the trunk, there is just a very small embedded control. Okay, I will not show the typical video about how it works, let's draw the conclusion. So my point is that next generation architecture, including the racing system that we are focusing at, will ever be more complex and workload intensive. You don't need to hope for a classic Intel-based architecture, but you need to comply with massively parallel heterogeneous parallel core platforms. The resources will be scarcest. The memory will be a big wall here. And one thing is designing your algorithm and your application. A way more difficult thing is to certify it, or at least qualify it for tight real-time guarantees. And yeah, to conclude, this is essentially our proposal. So let's try and focus together, not just on algorithm, not just on the best sensor fusion model, but let's try to do that also considering parallel requirements. We really are in need of parallelized system, parallelized libraries, qualified libraries that make limited use of unpredictable software. We try to advocate for these paradigms, and yeah, we try to implement them on our next generation racing platform. Thank you very much.
All right.